Final exam. All right. Time, May the 5th. It's Tuesday. From 6 to 8 p.m. Same classroom. All right, yeah. Then, part A, part B. So you know the content part A, part B, so I do not need to say another time. So part A, you know quiz, right? The same as our last quiz. Quiz number 6. Start at 8 p.m. Same day, okay? Yeah. Same day. Yeah, but I set the starting time at 8 p.m. All right. Part B, 7 of 10 questions. In that period, okay? Yeah. And 3 of 10 questions. And these 3 questions you select, okay? You select. You have freedom to select which 3 of the 10 questions online. Online, then due date. So due date, these 2, part A and this part B, 3 selected questions due end of Sunday of the same week. Okay? All right. Then, the questions are based on last 2 assignments, okay? Homework assignment 3 and homework assignment 4. Yeah. So after midterm, so you do not need to spend your time on homework assignment 1 and 2, just last 2 assignments. So that's the information I feel are, important for the final. So if you have any question, so you can let me know. Okay, yeah. All right. Let's look at the topic, fast Fourier transform. Yeah. When we, Justin.
I was just going to say, is part A of that also based on quiz number 3 and 4, or the second, the quizzes, the part A's of homework 3 and 4 as well?
Yeah, pretty much that. Oh, yeah, but let's see, quiz. I'll give you quiz 4 already, right? Quiz 4, did I give you for homework assignment number 3?
Wait. I think we've had 1 quiz and 1 homework going. So It's been homework 1, quiz 1, homework 2, quiz 2. We've had homework 3, quiz 3.
Yeah. You don't have homework quiz 4?
I don't believe so.
Oh, then I need to give you quiz 4 first, then quiz 5. Yeah. Oh, yeah. I thought I gave you. No, I didn't. All right. So I need to give you quiz 4 first.
Give us quiz 4.
Sorry, can you repeat?
I'm looking at Canvas, and it does say you gave us quiz 4 already.
Oh, okay. Yeah, I got confused. Yeah, I got confused. Yeah, quiz 3.
Oh, I'm sorry, the midterm was quiz.
Yeah, midterm quiz 3.
Okay, we are ahead. Yeah, all right.
Yeah.
We're caught up, rather.
Right, after midterm, yeah, because in my impression, I thought
Is your later quiz 5 then?
quiz 5 I know, I will do it soon, yeah, quiz 5.
So quiz 5 and homework 4.
4,
Thing, and then
right.
6 and final.
Yes, yeah.
And so the final part A is going to be based on quiz 4 and 5, just like the
Yeah.
other parts?
Yes.
Okay.
Yes.
That's all.
Yes.
Thank you.
Yes. Yeah. All right.
We'll have our answers to our homeworks and our quizzes
Yeah.
released by then.
Yes, definitely. Much earlier, I assume. Yeah. Well, I will release answer for quiz 4 soon. Yeah. All right. Yeah. Okay. Yeah. I hope it's not too complicated. All right. Mainly based on logic. Yeah. All right. Next. Property for computation efficiency. Yeah. So now we look at a calculation. Yeah. So we have the formulas. Discrete Fourier transform. The matrix multiplication. Yeah. So that's the formula, matrix multiplication. Yeah. All right. So for that formula, if we calculate matrix multiplication directly using our linear algebra way, that's not the most efficient way. That's not most efficient way. Because if we do using linear algebra formula directly, that's the general formula. The general formula does not consider the special structure of our Fourier matrix. Our Fourier matrix has a very special structure. Yeah. So we want to take advantage of the special structure to get a much faster calculation. Yeah. All right, so let's look at this. What's the special structure in our Fourier matrix? Yeah. When there are even number of samples. Yeah. So here, the first property we want to explore, we want to have even number of samples. So even number of samples more friendly than odd number of samples. Yeah. Because when we split, we have first half, we have second half. There is some symmetry property. We can take advantage to explore computation efficiency. Yeah. For odd number samples, we cannot take advantage of the symmetry property. That's the main reason. Okay? All right. Later, yeah, because later we need to look at the generality, right? Yeah? Because for the arbitrary given samples, only 50% even number of samples. Another 50% all number of samples, right? So if your method only works for even number of samples, that means your method works for 50% of the cases. Right? We want a method that works 100% of the time, not 50% of the time. Yeah. Don't worry. Yeah. The remaining 50%, we can easily make it work. We can make it work by doing small multiplication. Remember, so here I mentioned the golden rule of our problem solving. Remember, golden rule of the problem solving. when we have two cases, even case and odd case, even case easier for us to take advantage of the symmetry property. Odd case a little harder. Yeah, let's delay the harder case. Let's solve the even case first. After we get a solution, yeah, then we go to the odd case and we compare how much is the difference. Then we just fix the difference part. We do small extra work to fix that little difference part. Then we cover both cases. That's the golden rule of problem solving. Yeah. All right. Yeah. So let's do the even case first. All right. So let capital N, capital N, total number of samples. So capital N equals 2 times capital M. Yeah. So the capital M, because we needed this capital N, half of the capital N, we need to use it in our formula. We split our samples right in the middle, one half, first half, second half, symmetric. These two halves have some symmetry we can explore. Yeah. So we need also a capital M to allow us to use the symmetry property. Yeah. All right. Then little w, yeah. The first little w, based on the capital N, we have a little w expression. The second little w corresponds to capital M, so we have a corresponding expression. Yeah. So they're correlated. Yeah. Yeah, because capital N equals 2 times capital M. Yeah. So if you square W sub N, you get W sub M. So you have this relationship. Yeah. Sometimes you use the first W, sometimes you use the second W. Okay, all right. Yeah. You know, yeah. X, yeah, K. All right. Then Fourier transform, discrete Fourier transform. Vector, yeah. Vector in the frequency, yeah. This is a frequency spectrum, right? Yeah. We call the frequency spectrum. Yeah. So vector. All right. Yeah. And each entry of this vector can be calculated by this discrete Fourier transform. Yeah, that's the discrete Fourier transform formula. All right. And here, yeah. So the K here, yeah, because when you look at the subscripts, for the K, there are 2 cases. Even subscript, odd subscripts. Yeah. 2 halves. So you split. So you can split even coefficients and odd coefficients. All right. Signal. So our original signal. Yeah. All right. Then we split our original signal into 2 halves. Yeah. Even, right? So FEN. Yeah. So we use a vector collecting all the even samples. Yeah. The samples with even subscripts. The first vector. Yeah. Second vector, odd, F odd, OD, collecting all the samples with odd subscripts. Yeah. Yeah. Why we do it this way? Later you will see. In this way, we can explore some similarity. Yeah. When we look at the calculation formulas, we can discover some similarity property. So there is, yeah, so later I will explain. So there is some basic strategy we can use to save our computation resource. Now, here we do some exploration on the structure. Now, so the structure we split even samples and odd samples, two vectors. All right. Then, because when we look at the even sample vector, odd sample vector, the size, the dimension of the vector is exactly 1/2 of the dimension of the original vector, right? Yeah. Yeah. 1/2, exactly 1/2. All right. All right. So you have two vectors with half of the original size. All right. Then, this time, we use the divide and conquer approach. In this problem-solving situation, we apply divide and conquer approach. So we divide the original signal into two subsignals with half of the original size. Then we conquer each one. How do we do the conquering operation? We multiply the corresponding, this is the corresponding Fourier matrix. Capital F sub m, the dimension, m, capital M by capital M dimension. Okay? Much smaller than capital M by capital M. So think about, so here, look at the reduction process. All right. The capital M, M, so it is a capital M by capital M, the size, all right? Yeah. Capital F sub M, the size, capital M by capital M, okay? All right. Suppose this square is M by M. Yeah. Then we split. Okay. Yeah. M half size. So then this size 1/4 of the original square. That's M by M. See, you can see now suddenly when we do the divide and conquer, we split the original signal into two halves. Then when we do the matrix multiplication, we need the matrix we use the size 1/4 of the original size. Look at the reduction part. The 1/4 of the original size. Yeah. All right. Yeah. So then we, with this 1/4 size, matrix multiplication, so we apply the discrete Fourier transform. So we calculate frequency, even component frequency. All right. So even component frequency. But we use the capital F sub M multiply the even component of the signal, original signal. So that's the formula for the discrete Fourier transform. All right. Then for odd component of the frequency vector, so we do another matrix multiplication, discrete Fourier transform on odd component. Okay, all right. So that's the intermediate results. So this calculation is the intermediate result. So we prepare. So these two matrix multiplications, that's our preparation part for our end result. End result. We need another step to get the end result of the the frequencies. All right. So what's that? Then now the frequency, first half of the frequency, yeah, f hat n subscripts, yeah, so n subscripts and n plus m, that little n, all right? Little n goes through from the subscripts from 0 through capital N minus 1. That means the subscripts corresponds to the first half of our destination vector. Yeah, so we calculate. Yeah, so our discrete Fourier transform, yeah, first half and the second half separately. Okay, so n, but from 0 through n minus 1. Okay, so the second half, little n plus capital N. Yeah, yeah. So in this way. Yeah. All right. So then, how to generate the first half? Okay. All right. Then, so we use the. All right. So F even vector intermediate result. Okay. Intermediate result. All right. So FEN, yeah, so EN component, yeah, plus that little w, yeah, times the other component, all right, yeah. Then second one, yeah, so the even component minus that. So this little w, you know, the same thing, see? Yeah, same thing. The first one, same thing. But the first one plus, second one minus. Okay? All right. Yeah. So that's so these two, we combine, we get our frequency vector, final frequency vector. All right? So that's the formula. That's the, you know, fast Fourier transform formula. So here you can see. Yeah. We split. So actually we make, from paper you can see your formulas become more complicated, right? Yeah. So you do more things. Yeah. More things. But we reduce the size of calculation. Half of the size. We work on half of the size. All right. But you don't know, when you do more things, although each step you work on half of the size, how do you know when you put things together, you can do faster? How do you know that? Yeah. So we will prove. Yeah. So we will calculate the formula. How many multiplications? When we prove it, we need to count the number of multiplications we need. We want to show in this way we can reduce a lot of multiplications in this way. Then it's faster. Yeah. All right. Yeah. So next. All right. Before we move to next slide, yeah. So let me explain a little more on our goal. So here, our goal, we want to reduce the number of multiplications as much as we can. That's our goal. All right. So look at here. Okay, all right. These two multiplication independent, right? Independent. So first multiplication, second multiplication. Yeah. Because these two vectors are independent, right? Yeah, no relationship. Okay? Yeah. These two. All right. So we have to do certain number of multiplications here. All right. But at this side, all right. W, little w, this is a number, scalar number, right? Scalar number multiply this vector. So scalar number multiply vector. Yeah. We need to do multiplications, right? Yeah. But because these two expressions are the same, so we only need to do multiplication once, right? Yeah. So we do multiplication, scalar times a vector, you do certain number of multiplications, but when you use the same expression here, you just copy. Because you already have the vector, whole vector, right? So you reuse the vector you already calculated for the first half of the frequency vector. Yeah. So second time, retrieve, and you do subtraction. Do subtraction. Yeah. So in this place, you don't want to do redundant multiplication, right? Same multiplication, why you do twice, right? Only do once. So that's, so for our goal, we want to reduce the number of multiplication as much as we can. Yeah. Yeah. So we should be very careful to reduce the redundancy. Yeah. Okay? Never do unnecessary multiplications. All right, so that's from this slide. Next slide. Yeah. So we need to, look at so a little more. Yeah, so all right. For each frequency, yeah, so this is for individual frequency, all right? Based on the formula, we have this long expression based on the original formula, yeah, discrete Fourier transform. All right. Then we rewrite it based on the even odd terms. Yeah. So all the even terms, we put them together in the first summation, and all the terms, we put them together in the second half summation, but there is a common factor. Little w sub n, capital N, sup little n. Yeah. So we have a common factor. We factor the common factor out. Okay, all right. And for the upper one, yeah, because upper one, remember, for each little w, the exponent is an even number, right? Even number, then that's our little w sub m version, yeah? Yeah. So based on the property, right? Remember the property here, right? Yeah. All right, so we simplify slightly, yeah, slightly, all right. Then, the lower half also similar structure. Yeah. Similar structure, although there is a, common factor. Yeah. All right. All right. Then, when n greater or equal to m, yeah, because when you consider subscripts, sometimes, look at it here. So that little n, in the first half, little n less than capital M, right? But in the second half, your little n is greater or equal to capital M. Yeah. So we want to simplify the second half. No, second half, okay? Yeah. First half, we keep it. Yeah. Second half, we can simplify slightly, because we consider if n greater or equal, then we take out capital M, then the remaining part of number we put in little n. Okay? Yeah, because we can take out capital M. All right. So what's the benefit if we use this structure? The benefit is when we calculate, little w, because we need to calculate. Yeah. Then, so we can split the little w in these two parts. Yeah. The second little w part based on, half n. So little w m, so here, all right. Yeah. Right. So m here, yeah, that's 1, right? Yeah. So based on the definition of little w, yeah. So this is 1, but here, little w sub capital N super m is 1/2, so that's negative 1. Yeah. 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 So this is, cancellation, yeah, 2, negative pi I, negative 1. Yeah. So that is the negative. Yeah. That means you just change the sign. Okay? Change the sign. Yeah. All right. Yeah. So the first half, yeah, see? Yeah. So this half. All right. Yeah. So let's see. Yeah. Yeah, n, right. Yeah. Okay. Yeah. All right. Yeah. Now, so we're here. Yeah. All right. Calculate. Yeah. So now, here. Removing the redundancy. Yeah. All right. Split. Yeah. All right. Split. First half, second half. All right. The first half comes from this formula. Yeah. So that we have to do this matrix multiplication, have to another matrix multiplication, but later you will see. Yeah, remember. Yeah. So here, you need to do this matrix multiplication here. You also need to do matrix multiplication here, but you can see the structure of matrix multiplication, is it the structure similar to the structure of capital N times F vector? Yeah, structure-wise, the same, right? Yeah. That means when you do matrix multiplication here, you can use recursion. You can split another time, right? Half. So that's by recursion. Yeah. So you do not do the direct matrix multiplication, because after you split half, you can have another round saving. Each round, when you do split, you have saving. Yeah. So the idea is divide and conquer. Divide and conquer. How do you conquer? You do conquer by recursion. This recursion corresponds to the conquer step. How do you do the conquer? By recursion. Recursion is the conquering part. Okay? Yeah. All right. Yeah. So here, yeah, because after recursion we have that, we just reuse it. Okay? Yeah, here. We don't call recursion another time, all right? Yeah. So you need to call recursion here, but reuse the previous result. Okay? Here, reuse the previous result. Yeah. Yeah. So no recursion in these two places. Okay? All right. All right. Yeah. So then, after that, so here we use the idea, reuse the resource idea. Every time when we have the intermediate results, these two vectors, intermediate vectors, okay? So these intermediate vectors, we need to reuse them. So we save the intermediate results to be reused. Yeah? Yeah, because in other places, we need to reuse the intermediate results. Okay? So we can save. We can avoid redundant. Yeah? Because if you do recursion, you take the redundant calculation. Yeah. So we avoid redundant calculation in these two places. Yeah. All right. Yeah. Yeah. So no new multiplication. Yeah. And this, because this little w multiplication, in the first half, you do the multiplication, right? Yeah. So this second half, you do not redo the multiplication. Yeah. Yeah. So you just copy the whole vector, you do subtraction. Yeah. Addition of two vectors, subtraction of two vectors. No multiplication. Yeah. So this place, no new multiplications. Yeah. All right. Yeah. Next, now we need to estimate the number of multiplications when we use this new algorithm. Yeah. We do divide and conquer, recursion. It looks like it's so complicated, right? So how do you know how many multiplications you need to do in this way? You don't know, right? Yeah. So this last thing we need to do, we need to estimate the total number of multiplications using this fast Fourier transform. Yeah. All right. So we need to derive a recurrence relation for the total number of multiplications. All right. Yeah. So, yeah. So that means we use divide and conquer approach to calculate this capital F matrix multiplication. All right. Before we do it, now let me ask you, before we start it, let me ask you, how many multiplications if we do the direct matrix multiplication? If we do not apply fast Fourier transform, we do just a matrix multiply this vector using the linear algebra definition of the matrix multiplication. Yeah. So capital N squared, right? Yeah. Because this matrix has capital N squared entries, right? Yeah. 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 Okay, so now row times column. Okay. Each row you have capital N entries. Now you multiply vector, so you have capital N. Yeah. So each row you have capital N. But you have n rows, right? And capital N times capital N. So you have capital N squared multiplications if you do not apply fast Fourier transform. All right. Now let's look at, if we apply fast Fourier transform, how many multiplications do we need? We need to calculate this matrix multiplication. All right. So here we use this capital H matrix of n to represent total number of multiplications. All right. But this time you calculate capital F sub m matrix multiplication. So based on the definition of this function, it should be capital H of capital N. Okay. Yeah. So, all right. That's for this vector, right? Yeah. But you have another vector you need to calculate. Yeah. So you need to do another vector multiplication, but then another multiplication, right? Yeah. So here, look at how many multiplications do you need. All right. Yeah. So, all right. Yeah. Although you can put inside. Yeah. Inside. So you calculate the vector inside the parenthesis first. Yeah. That's m multiplication, right? Because the size of this f is m multiplications. All right. Then you do this matrix multiplication with this vector based on our capital H. It's capital H of m plus this m multiplication here. Okay. All right. So after you split into two halves, you need to do the total number of multiplications, this many. Okay? All right? So let's put them together. We have a recurrence relation. Yeah. Capital H of capital N. Yeah. We, based on divide and conquer, yeah. So conquer, this part is conquer. So more recursion here. Okay? So based on divide and conquer, yeah, we need to do 2 times capital H of capital M plus M. But we need to have a base case. So what's the base? Capital H of 2 equals 1. Yeah. Capital H of 2, yeah. So you only have 2 samples. Yeah. So you do 1 multiplication. Yeah. All right. Then we need to solve this recurrence relation. Yeah. So not too hard. Yeah. Let me show you how to solve. Yeah. But when we solve it, yeah, we want to consider a convenient case. Capital N is a power of 2. Convenient case. Yeah. If it's not power 2, yeah, so don't worry. We have a way to work it around. Yeah. Remember the golden rule. Yeah. So here we apply golden rule. Another time, power of the 2 case, that's the simplest case. So let's make it work. Then, if it's not power 2, modify. We modify to make it work. Yeah. All right. Yeah. So P equals log base 2 of n. Yeah. So capital M equals 2 to the P minus 1. Yeah. Then our recurrence relation, so this time, we can get a sequence of equations, yeah, like this, okay? Like this. Look at the structure here. We can do iterations, yeah, iterations, okay? All right. Yeah, keep doing iterations, all right? Yeah. Then the last equation, yeah, capital H of 2 to the first over 2 to the first, yeah, there, because after a certain number of times, yeah, here, how to keep track of the numbers? Yeah, let me show you how to keep track of the numbers. The exponent number P minus 1 plus 1 equals P. Okay? P minus 2 plus 2 equals P. We call it invariant. This property we call invariant. Okay? It's true all the way to the end. 1 plus P minus 1, fixed number P, invariant. Okay? In this way, we can keep track of the critical numbers. Yeah. All right. But this is 1/2, right? Yeah. So then the whole thing is P over 2. Yeah. All right. Then at the end, we have this, yeah. The last thing we have 1/2 times capital N times log base 2 of n. Yeah. So this tells us if we apply fast Fourier transform, the number multiplication we need is this many comparing with capital N squared. How much is the improvement? How much is the improvement? Okay? Yeah. Right? Yeah. All right. Yeah. So here, let me just use the last 2 minutes. Yeah. So I do not want to, so I want to use last 2 minutes to convince you the improvement is big from n squared. Yeah. So here, let's ignore 1/2. We only compare this n times log base 2 of n. Okay. All right. Now I want to use this when capital N equals 1,000. How much is the improvement? Okay. All right. In this case, capital N squared equals 10 to the 6th, right? 10 to the 6th. 1 million. 1 million. All right. Then, what is capital N times log base 2 of capital N? We use approximation. 10 times 10 to the 3rd, but log base 2 of n, this is 1,000. We know 1,000 approximately equal to 2 to the 10, right? So here we, use approximation, 1,000. So that is 10, right? Yeah, because, 2 to the 10. So that's 10 to the 4th. So what's the ratio? You have the ratio here. You can see 100 to 1 ratio, right? Yeah. So you use the number of multiplication 1/100th of the original multiplication. 1%. Yeah? That's improvement. If you do the calculation on 1,000 samples, the number of multiplication, that's 1% of the original multiplication. How big is the improvement? 1%. You can do the same thing with 1%. That's That's why fast Fourier transform. Later, when you use the software, yeah, so you never need to do it by yourself. Okay, you apply the software. That's the reason. The algorithm, very fast. Okay? You can save a lot. Okay, all right, that's it.